let's say if we have this geometric sequence right over here. And geometric sequences, they can go on forever, or there can be a finite amount, but let's just say they go on forever. And this is denoted with the dots at the end. So what is my common ratio for this geometric sequence? Well, first let's take a look at an easier example. So if I have this geometric sequence right over here, my common ratio is going to be 2. The common ratio refers to the number you have to multiply by to get from one term to the next term. In order to get from 2 to 4, I have to multiply by 2. If I want to get from 4 to 8, I have to multiply by 2, right? So it's just this constant number you have to multiply by to get to the next term. And your common ratio, for example, let's say if I have 1/2, 1/4, 1/8. You might think my common ratio is 2, right? Because in order to get from 1/2 to 1/4, well, one thing I can do is I can divide by 2, right? But in this case, this is going to be wrong. My common ratio is actually going to be 1/2. Term to the next term, you have to multiply by some number. In this case, in order to get from 1/2 to 1/4, I have to multiply by 1/2. So the thing about common ratios is it's always going to be multiplication of some number, never going to be division. Now notice how if I take any term here, but let's just simplify it. Let's say if I take my 4, my second term, and I divide it by my first term, which is equal to 2, right? My first term is 2, my second term is 4. Notice how when I divide my second term by my first term, I get my common ratio, which is 2. So let me just write this down, actually. If I divide my second term by my first term, I get my common ratio. All right, that's something important to know. But it turns out that you can do this for any number. So if I take my fourth term, for example, and divide by my third term, notice how 16 divided by 8 gives me 2, which is also my common ratio. So it turns out that if you divide a sub n by a sub n minus 1, you're going to get your common ratio. Okay? So if you take any term and you divide it by the term before it, you're going to get the common ratio. But just to simplify things, let's just say you're dividing the second term by the first term. Put this to use. So, for this example, I made it kind of easy, but what you're going to do is you're going to take your second term and you're going to divide it by your first term, which in this case is 1. So anything divided by 1 is just itself. So that's our common ratio. But notice here, right? If I want to get from my second term to my third term, look what happens. Let's say if I just wanted to check my work, okay? I want to check my work to make sure this is correct. So let's see if this is correct. So if I have a squared b squared over 3 and I multiply this by a squared b squared over 3, what am I going to get? A squared times a squared gives me a to the 4th power. Right? If you have the same base for your exponent, you just add up the exponents itself. So since these two a's are the same base, all I have to do is just add up the exponents. So 2 plus 2 gives me 4. Same is the case for the b exponent, right? And then 3 times 3 gives me 9. And notice here, right? That is exactly what's going on. And you can apply the same logic for this. So this is indeed what is the common ratio here? Well, remember, just have to take your second term and divide it by your first term. So in this case, my second term is actually going to be x squared, y squared, z. And I divide it by my first term, which is xy. So x cancels out. This cancels out. So you just get that your common ratio is just x, y squared, z. The thing we did here was so it was x squared, which you can write as x times x. And you have y to the 3rd power, which is y times y. And you multiply this by z, right? And you're dividing this by xy. So notice how one of the x's cancel out. So you're just left with x to the 1st power. And notice how one of the y's cancel out. So you're just left with y to the 2nd power. So, that's basically what happened. And yeah, that is our answer. So, you can check the work here, right? You can plug in, in order to get from my first to my second term, you can just check that by multiplying this. In order to get from my second to my third term, you can also check by multiplying this. But, this is just kind of the simple concept of getting the common ratio in geometric sequences. Now let's learn about recursive sequences. Recursive sequences are very weird. They can be a arithmetic sequence, meaning that, remember back to the arithmetic sequence, so it's something like 1, 2, 3, 4, right? You just add on a common difference every time, right? Just add a number every time. Recursive sequences can be geometric, so like the example that I showed before, where you multiply by some number. So this right over here is an arithmetic sequence. I just want to make that clear. So this is arithmetic. I'm just going to put A there. This right over here is geometric. So I'm just going to symbolize this with a G. Or recursive sequences can actually be neither. So this is something weird about recursive sequences. They can be neither. So an example of a sequence that's neither arithmetic or geometric is the Fibonacci sequence. And this is actually pretty cool. So what you basically do is, okay, let's say we start out with our first term being equal to 1 and our second term being equal to 1. Okay. Now, in order for us to get to the next term, what we do is we add these two numbers together. So 1 plus 1 is equal to 2. In order to get from my third term to my fourth term, I multiply the previous two numbers to get to 3, right? In order to get from my fourth term to my fifth term, I add the previous numbers before the fifth term, the two previous numbers before the fifth term, right? And then you see this pattern, right? So in order to get from this to 2, right? 1 plus 1 gives me 2. 1 plus 2 gives me 3. 2 plus 3 gives me 5, right? If I wanted to get to the sixth term, well, I would have to multiply the fifth and the fourth term, right? So 3 plus 5 gives me 8. 5 plus 8 gives me 13. And you kind of see the pattern, right? And the way you actually write the Fibonacci sequence is if you have a sub 1 is equal to 1, your first term is 1 and your second term is 1. Well, all you have to do is you would have to say, if I wanted to find out the nth term, what I would do is I would add my previous term with the term previous that term. So let me just show you an example of how I can apply this. So let's say if I wanted to find out the third term of my Fibonacci sequence. Well, a sub 3 is going to be equal to a sub 3 minus 1, right, plus a sub 3 minus 2. All I did here was I just replaced all of the n's with 3's, right, because I'm trying to find the third term. A sub 3 minus 1 is a sub 2. A sub 3 minus 2 is a sub 1. So notice how this term is directly behind a sub 3, and then this term is 2 steps kind of behind a sub 3. We know a sub 2 is equal to 1, so we can substitute that in here. We know a sub 1 is equal to 1. We can substitute that here. 1 plus 1 is 2. 1 plus 1 is 2. And notice here, right? Our third term is indeed 2. So if you keep doing this process on and on and on forever, well, you know, you're going to get this Fibonacci sequence. And yeah, the Fibonacci sequence goes on forever. Now, recursive sequences are weird. In an arithmetic sequence, if you want to find out the nth term of the sequence, it's going to be equal to your first term plus n minus 1 times your common difference. If I wanted to find out the nth term of a geometric sequence, for geometric sequences, the formula for finding out the nth term is a sub n is going to be equal to the first term times the common ratio to the n minus 1 power. All right. For any of these two formulas, right? For any of these two formulas, if I have a sequence, and let's say if I wanted to find out the 44th term, well, all I have to do is just plug in 44 for n, and I don't have to go through that manual process of just doing kind of, if I have, let's say, a sequence like this. Let's say if I have an arithmetic sequence, like 1, 4, 7, 10, and I wanted to find out the 44th term. I do not want to list out 44 terms, right? That's going to take forever. So I could just use this formula, right? So think about these two formulas as like a shortcut for finding out the nth term of a sequence. Now, the thing about recursive sequences is there's actually no shortcut for this. So for recursive sequences, the thing you got to know is that there's actually no shortcut for finding the nth term. Now, what the hell do I mean by that? All right, so we're given a sub 1 is equal to 3, and a sub n is equal to a sub n minus 1 plus 3. And I want to find out what a sub 4 is equal to. What is this equal to? Well, let's start doing the math. So if I know my first term is equal to 3, well, in order to find a sub 2, this is just going to be equal to a sub 2 minus 1, right? Because if I want to find out a sub 2, everywhere we see an n, we replace it with a 2, right? So it's going to be a sub 2 minus 1 plus 3. A sub 2 minus 1 is equal to a sub 1, and a sub 1 is equal to 3. So 3 plus 3 gives me 6. Now that I know a sub 2 is equal to 6, I can find a sub 3. So a sub 3 is going to be equal to a sub 3 minus 1 plus 3, right? And then I have a sub 3 is equal to 3 minus 1 is 2. So I get that a sub 3 is equal to a sub 2 plus 3. We know that a sub 2 is equal to 6, so we can substitute that in. So 6 plus 3 is just going to be equal to 9. And then finally, I can find a sub 4. So a sub 4 is going to be equal to a sub 4 minus 1, which is equal to 3 plus 3. And then after that, I can substitute 9 in for there. So 9 plus 3 is equal to 12. Okay. Wow, that was pretty annoying. But notice how for a recursive sequence, right, there is no shortcut. That's the thing. That's the thing about recursive sequences. There's no shortcut to this, sadly. So the thing about recursive sequences is, let's just say, for example, right, I plugged in 4 immediately. So let's say if I did not know what a sub 3 was equal to. Let's say if I did not know a sub 3 was equal to 9. Okay, let's just say I did not do any of this work. If I plug in a sub 4, n is equal to 4 into my formula, I would get a sub 4 is equal to a sub 4 minus 1, which is 3. And then this is going to be plus 3. You got to remember this, okay? For a recursive sequence, you have to know the term before it in order to get a term. So if I wanted to find out, let's say a sub 48, let's say if I wanted to find out a sub 48 for this sequence, well, this is going to be equal to a sub 48 minus 1, which is 47, and then plus 3. So if I wanted to get a term, I would need to know the term before it in order to get that term. So if I wanted to find the 48th term, I would need the 47th term. If I wanted to find out the 4th term, I would need the 3rd term. Right? So clearly, there's no shortcuts because, then after that, you have to find out what the 3rd term is equal to. But to find out the 3rd term, you would need to know what the 2nd term is equal to. And you kind of see like the pattern, right? So yeah, give this a try. Right, so kind of just proving this to you, right? So if I plug in n is equal to 3 into this formula, right, just to kind of show you guys everything. So if I plugged in n is equal to 3 into this formula, I would get a sub 3 is equal to 2 times a sub 3 minus 1, which is 2, plus 1. But notice how we don't know what a sub 2 is equal to. So, once again, just repeating the same idea that there's no shortcuts for recursive sequences. You have to know the previous term before finding out the actual term. So let's do it. So let's find out what a sub 2 is equal to. A sub 2 is going to be equal to 2 times a sub 2 minus 1. So 2 minus 1 is 1 plus 1. We know a sub 1 is equal to 1. So let's substitute that in here. 2 times 1 is 2. 2 plus 1 is 3. And we know the 2nd term is 3. Now let's find a sub 3. So a sub 3 is going to be equal to 2 times a sub 3 minus 1. So that's going to be 3 minus 1 is just 2, and it's going to be plus 1. Now that we know that a sub 2 is equal to 3, right? Now that we know the previous term, then we can find out a sub 3, which is equal to 7. All right. But I also want you to notice something else, right? We got the answer for this recursive sequence, but notice something else, right? If I list out the terms, if I list out the terms right here, this sequence is actually neither an arithmetic sequence or a geometric sequence. So I also want to keep that in mind, right? In our recursive sequence right over here, we're multiplying by a number, and then we're also adding a number. So this sequence right over here is neither arithmetic nor geometric. All right, now here's how to convert from a recursive sequence to an arithmetic sequence. So in order to convert from a recursive sequence to an arithmetic sequence, the first thing you want to look out for is if our recursive sequence is arithmetic in the first place, right? If my sequence is not arithmetic in the first place, how can I convert it into an arithmetic sequence looking in this form, right? And this form right over here is also kind of known as like the explicit form because you're kind of explicitly stating out like, you can find out like, let's say the 44th term by just substituting 44 into the formula. So this is sort of known as the explicit form. So let's try to find out how to convert from recursive arithmetic sequence to an explicit arithmetic sequence form. So one way to convert from this to this is, well, we can list out the terms. So if we know a sub 1 is equal to 3, well, a sub 2 is going to be equal to a sub 2 minus 1, which is 1 plus 4. A sub 1 is 3, so 3 plus 4 is just going to be equal to 7. A sub 3 is going to be equal to a sub 3 minus 1, which is 2, plus 4. A sub 2 is equal to 7, so let's substitute that in. 7 plus 4 is equal to 11. And if I list out the terms, now, if I list out my terms, right, I know a sub 1 is equal to 3. My second term is going to be 7, right? And my third term is 11. Notice how every term I'm adding 4. Every term I'm adding 4 to it. So I can actually state this explicitly. So I'm going to get a sub n is going to be equal to my first term, which is equal to 3, plus n minus 1 times the common difference, which is equal to 4 in this case. And that's our answer. So now, if we wanted to find out a sub 44, all we'd have to do is just, plug in 44 into n, and then we can solve for it. So yeah, that's kind of how you do these types of problems, right? We know that our first term is equal to 3, so immediately we can substitute that in for the a sub 1 part, right? Which we did here. And we found out the common difference is 4, so immediately we can substitute that here. So once you know the trick for doing these types of problems, it's actually pretty easy. Because look, like if for example, let's say if I have a sub 1 is equal to 5, and let's say I have a sub n is equal to a sub n minus 1 minus 10. Well, if I wanted to convert this into this form, right over here, well, I know that my first term is equal to 5, so I can immediately substitute that in. And I know my common difference, well, that's going to be 10, right? I mean, in this case, negative 10, right? So immediately I can substitute that in there, and there we go, right? So, I mean, if you're still unsure about this, you can list it out and see for yourself, but this is kind of the way to do it. I mean, you can use this formula for geometric sequences. So to convert from recursive to kind of standard geometric sequence, well, you can just use this formula. For example, if I have my first term is equal to 3, and then my, let's say, a sub n is equal to 2 times a sub n minus 1. Well, notice how if I wanted to get to a certain term, I would have to multiply my last term by a common difference, a common ratio, which is 2 in this case. So in this case, my common ratio is 2. So that's going to be my common ratio. And I know my first term is equal to 3. So I can just substitute this into the formula. So I get a sub n is equal to 3 times 2 to the n minus 1 power. And we're done. But you can also confirm things out for yourself. So let's say if we wanted to find out what a sub 2 is equal to, right? Let's just check our work. And it's, extra practice. So a sub 2 is going to be equal to 2 times a sub n minus 1. So a sub 2 minus 1, which is 1. And we know that a sub 1 is equal to 3. So substituting 3 in for this, we get 2 times 3, which is 6. If I want to find out a sub 3, well, same process. It would be 2 times a sub n minus 1. So a sub 3 minus 1 is a sub 2. A sub 2 is equal to 6. So substitute that in here. 2 times 6 is 12. And look. A sub 1 is equal to 3. My second term is equal to 6. My third term is equal to 12. Notice pattern. Yeah. So that is how you do it for geometric sequences.